All right, welcome everyone. Thank you so much for joining us today for the Grasp on Robotics talk series. I'm Rahul Mangharam and I'll be your faculty host for today's talk. We're also joined in by Dr. Johannes Betz and ZG, who will serve as the panelists after the talk. So as a quick reminder, previously recorded talks can be found on our YouTube channel and website. And throughout this talk, please submit your questions using the Q&A button at the bottom of your screen. These will be answered during the Q&A panel at the end of the talk. So I'm very excited to invite and have Dr. Andreas Malikopoulos, who is the Terry Connor Kelly and John Kelly Career Development Associate Professor in the Department of Mechanical Engineering. And he directs the Socio-Technical Systems Center at the University of Delaware. So I've known Andreas for many years, and he's doing very exciting work, and his research spans several fields, including the analysis, optimization, and control of cyber-physical systems, which we call CPS, decentralized stochastic systems, stochastic scheduling and resource allocation, and learning in complex systems. So prior to coming to academia, Andreas was the deputy director and the lead for sustainable mobility team of the Urban Dynamics Institute at Oak Ridge National Laboratory, one of the DOE labs, and a senior researcher at General Motors Global R&D Center. He received his diploma from the National Technical University of Athens in Greece and did his master's and PhD in Michigan, Ann Arbor, actually around the same time as I did. And Dr. Malikopoulos is the recipient of several prizes and awards. In 2019, most recently, he got the IEEE Transportation Systems Young Researcher Award and the 2020 University of Delaware's College of Engineering Outstanding Junior Faculty Award. He's also served on many editorial boards for transactions, IEEE transactions for intelligent vehicles, transportation, and he's been a steward for the sustainable cities and a member in the controls community. So welcome, Andreas. We're really looking forward to your talk today.
Great. Thank you, Rahul, for the kind introduction, and thank you for having me. It's great to virtually be visiting UPenn today. So what I plan to do today is to discuss how we can separate learning and control tasks in cyber-physical systems, and the motivation for this separation is to make to be able to eventually combine both the learning and control approaches. The world is changing, and one particular sector that undergoes significant changes is transportation. We're about to depart from conventional vehicles with internal combustion engines and move on to pure electric vehicles. And this transformation creates several opportunities and challenges. For example, we need to upgrade the existing infrastructure of our transportation network with high charging, high chargers. We need to develop control technologies that can coordinate the increasing demand for electricity from the vehicles and reduce the load for the power grid. We have opportunities to integrate the electric vehicles with commercial and residential buildings and create eventually off-grid buildings. On top of that, with the introduction of connected and automated vehicles, we can use the shared information from the vehicles and infrastructure and use this information in order to improve transportation efficiency, reduce congestion, and stop-and-go driving. So the common theme of these applications is that we use a cyber component, data or shared information, and we use this cyber component to control physical entities. So in other words, we have typical cyber-physical systems. Now, somebody might ask why we should be focusing so much on transportation. Well, in 2017, the United States consumed on average 19.96 million barrels of petroleum, and transportation accounted 71% of that usage. That's enough fuel to fill up the Empire State buildings over 2 times per day just to propel vehicles in the United States only. So you can see the impact of transportation on a global basis on oil displacement and on the environment. So with the introduction of connected automated vehicles, which are typical cyber-physical systems, we do have the opportunities to reduce oil displacement, improve transportation efficiency, improve the environment, at least reduce the impact on the environment, and eventually contribute to the health of the planet. So what I plan to do today is to focus on cyber-physical systems related to transportation. And then I'll go through several learning and optimal model-based control approaches that I have worked on over the last several years on emerging mobility systems. So I'll show you how we can make the engines of vehicles to learn how to improve their operation with respect to the driver's driving style. Then I'll talk about how we can develop model-based control approaches to coordinate connected automated vehicles. And through this, going through all these applications, I will try to highlight some of the challenges that we can encounter using learning or model-based control approaches. And at the end, I will try to convince you that if we can separate what we can control and what we can learn, then we can combine both and address some of these challenges. Before I get to the technical talk, let me acknowledge the contributions of my students in the IDS lab. In the IDS lab, we develop theories and algorithms that can make CPS able to improve their performance over time while interacting with the environment. And the focus is more on applications related to transportation, socio-technical systems, social media platforms, and so forth and so on. To test our algorithms related to transportation, we have developed a test bed, a robotic city. This is 20 by 20 feet long, or 6 by 6 meters for those who are familiar with the SI system. And we have about 50 robotic cars that we built in-house, and about 10 crazy flyers, drones that we can use. And we use this testbed to go beyond simulation, prove concepts in transportation, use the drones, for example, to act as coordinators that can collect data from vehicles and provide assistance to vehicles. We have used this testbed to show and demonstrate first last mile delivery options, like having, as you can see here in the video, a drone coordinate with a vehicle so that the drone is supposed to pick up a package from the building and coordinate with a vehicle and drop it off. We use also this to prove applications, concepts on applications related to connected automated vehicles and how we can use the drone on intersection, for example, and coordinate vehicles to cross the intersection without the need of traffic signals, and so forth and so on. We have also integrate into our robotic cars driver emulators, and we can drive these cars in our city. So as you can see here, we have the cameras ahead of the car, so the student can drive the car and see what's going on through a monitor. And with this setting, we can have a mixed traffic environment with connected automated vehicles and human-driven vehicles, and then address the in-between and how we can address the human driving behavior through the connectivity and automation. Dealing with a city, we encounter several challenges every time. So we thought, why don't we build a digital replica to use with a digital replica in a simulation environment, test our algorithms there first, and then once the algorithms become mature, then move on to the physical entity. And so we built a digital city, a replica of our scale city. And now we can also use this digital replica with our collaborators. They can use this, which is available online, and to test their algorithms. And then once the algorithms become mature, they can come to UT and do some physical testing. More recently, we also developed an app to test shared mobility in our scale city. So if somebody visits our lab, he can download this app, and then he can request any of the 50 robotic cars to take a ride, free ride. We don't charge anything at the moment. To our scale city. So with this app, we can prove some concepts that we develop in some optimization algorithms for eco-routing approaches, using the model of Uber and Lyft. We also have a driver simulation testbed that we use commercial software to do some simulations in our before we move to our scale city. So with this brief introduction, let me get back to our technical discussion. As I said, over the years, I have worked on several applications in transportation. I started with my dissertation when I work on how we can develop learning algorithms that can make the engine of a vehicle to learn to improve its performance while interacting with the driver. Then I moved on to plug-in and hybrid electric vehicles and develop power management control for these vehicles to maximize the efficiency. And over the last several years, I've been working on connected automated vehicles and how we can use model-based control and use the shared information from the vehicles to improve transportation efficiency and safety, of course. So as you can imagine, over the next several minutes, I'll tell you my story. I will start with my dissertation research and the learning of the engine and go all the way up to today. And I will try to highlight all the challenges I have gone through over the years using either learning based approaches or model-based control approaches. And then I will use these lessons learned over the years to convince you that if we can separate learning and control, then we might be better off. So the first chapter of my journey started in 2003 when I arrived in Ann Arbor, Michigan. I started in the winter semester in Michigan. You have this option. So it was December of 2002, I'm sorry. And it was about Michigan, Ann Arbor had about 11 inches of snow. So the first thing that I had to do is to buy long woolen socks. And the second thing that I had to do is to find a topic for my dissertation that will keep me busy over the next several years. So I started reading some articles and going through different papers. And then I realized that there is a common question among several people at that time. They all wonder how we cannot achieve the miles per gallon posted on the winter sticker. So I thought that this is a very interesting question, and that can keep me busy for the next 5 years. And I started digging into this question. So when we buy a vehicle in US, it comes with a winter sticker that gives us the miles, the fuel economy estimates for a high driving and cityway, driving. And although we can always achieve the estimates corresponding to the highway driving, we can barely achieve those fuel economy estimates for the city driving. So let's see why is this the case, why we cannot get the fuel economy estimates when you drive your car in the city. To understand engine operation, we need to look at the engine operation domain consisting of the engine torque and speed in conjunction with a brake-specific fuel consumption map, which is the BSFC map, which is those contours that you can see on the plot. The BSFC maps give you the fuel economy per unit time, right? So the less the value, the better the fuel economy. Now, the way that the OEMs optimize engine today, they take the engine operating domain, they discretize it to a finite, usually small number of steady-state operating points. Steady-state operating point means that you operate the engine at constant torque and constant speed. And then they compute the optimal variables of the controllable variables of the several that exist in the engine, like ejection timing, spark timing, VGT, EGR, you name it, with respect to these steady-state operating points. And then they come up with a map, and then they take this map and put it in the electronic control unit of the engine. So as you drive your car and you accelerate, as you can see on the top of the plot, then the engine jumps for operating point to operating point on the BSFC map, and then the engine interpolates values of the controllable variables corresponding to the steady-state operating points to optimize the engine. However, some of my colleagues at Michigan at that time did some experimental work, and they discovered the following. If we operate the engine at a constant torque and speed, right, fuel consumption is steady. And this is why we can achieve the fuel economy estimates on a highway driving, because on a highway driving, we essentially operate the engine at constant torque and speed. And this is why it's always beneficial to operate your vehicle with a cruise controller. However, if you approach this operating point from a sequence of operating points, then fuel consumption is varying. And moreover, if you approach this operating point from a different direction, then fuel consumption is associated with different values. So what happens when we drive the car in a city, we operate the engine under these transient operating points, which the engine has not optimized for. And that's why we have the discrepancy between how we drive and the fuel economy posted on the window sticker. Now, to optimize the engine over these transient periods a priori is infeasible, simply because every driver drives different, so we have an infinite class of driving styles. So what I did in my dissertation, I thought instead of focusing on the steady state operating points, let me focus on the engine operating point transitions. And the natural model to address this, to capture this, was the control Markov chain. So I modeled the engine operation as a control Markov chain, the evolution of the operating points as a control Markov chain. And then I developed a self-learning controller, and I was learning the transition probability matrix and transition cost matrix. And then I formulated the stochastic optimal control problem, and I was deriving a look-ahead control policy in real time while the driver drives the vehicle. So essentially, with this approach, the more you drive the car, the better the fuel economy becomes with respect to your driving style. We did several studies and several simulation results, and we show that we can improve fuel economy by at least 8%, just by doing a better calibration of the engine using learning techniques. I recently heard from University of Michigan that they have ongoing discussions with some tech giant from Silicon Valley who are leaders on autonomous cars. So apparently they plan to license this technology and move it on to their own autonomous cars. So this project attracted considerable attention at that time and had several discussions with the big three, GM, Chrysler, and Ford. So I eventually ended up working working with GM R&D. That was my first job right after graduation. So when I joined GM, they were working on a new combustion technology, and they wanted to depart from expensive piezoelectric fuel injectors and employ a simple and much less expensive solenoid fuel injectors. But with a solenoid fuel injector, you have injector-to-injector variation. These are four solenoid fuel injectors characteristic curves. And you can see the deviation between injector to injector at two different cylinder pressures. So with that technology, we wanted to have precise injections at the small fuel mass, so multiple fuel injections essentially. So we needed to make sure that we have very precise injections when we want to inject like 4 to 6 milligrams. So my job was to come up with a learning model that can learn this curve. And you might think the characteristic curve. And you might think that this is a kind of straightforward project. You can definitely get data and come up with a polynomial meta model that can give you this. However, the challenge in the engine is that I don't have measurement. I cannot measure the amount of fuel injected from the fuel injector. So I had to combine several supervised learning techniques using data that I have offline from fuel injectors with real-time adaptive control in order to learn the fuel injector characteristic curve in real time in fuel cycles. So with this approach, essentially, I was able to learn the curves for small injectors with just fuel cycles, which means in a few milliseconds. And on top of that, the scheme was able to essentially also capture the day-to-day variation due to the environmental conditions. So that was another project that I used learning techniques, a combination of learning and adaptive control techniques. And this approach resulted in about 4% improvement in fuel consumption, which is quite significant for engines. So that was around 2010. And then we have the 2010 volcano eruption in Iceland. And you might wonder, how is this related to this discussion? Well, believe it or not, this volcano eruption changed my career path and also the research direction. In 2010, I was invited to participate in the 2010 German-American Frontiers Symposium hosted by National Academy of Engineering. And due to the volcano eruption, several speakers from Germany could not make it to the US. That was hosted by Oak Ridge National Lab in Tennessee. So the organizers asked me to give a seminar, and there were several folks from Oak Ridge in the audience. And one thing led to another, and I ended up working for Oak Ridge National Lab and moving on to hybrid electric vehicles and plug-in electric vehicles on my research. So when I joined Oak Ridge, my first project was to develop an optimal power management control algorithm that can maximize the efficiency of hybrid and plug-in hybrid electric vehicles. So let's see what is a hybrid electric vehicle. In a hybrid electric vehicle, in addition to the engine, we have a motor, generator, and battery that can power the vehicle either separately or in combination. So essentially, if with the hybrid electric vehicles, we can deliver the power demanded by the drivers either through the engine or through the motor, or by combining engine and the motor. When we use the motor, we deplete the battery. So we need to make the engine operate the generator and charge the battery. So there is a lot of decision-making process going on while the driver drives the vehicle. And just to give you a flavor of this problem, the first thing that we need to do is to identify the feasible state and control action pairs for each of the subsystem, engine, motor, generator, and the battery. And then we formulate an optimal control problem when we want to maximize the efficiency of the entire system or minimize the cost of the entire system. And we use the long-run average cost per unit time just because we want to optimize the operation of the hybrid electric vehicle in long term, as the driver drives the vehicle for days or for months. Now, to solve this problem, there are two major challenges. First, you can't really solve this problem on board the vehicle. On a commercial vehicle, you can barely inverse a 4x4 matrix. You don't have the computational power to do that. The second challenge is that even if you solve this problem, the optimal control strategy will be optimal for one driver only. I mean, if any other driver drives the vehicle, then you have different results. So to address these problems, I reformulated the problem as a multi-objective maximization problem, where I was trying to maximize the efficiency of the engine, motor, generator, and the battery. And then I solved this problem offline for every different realization of the state of the system, and I computed the Pareto optimal point for each of these different realizations. And then I came up with a map and operated the system, the vehicle, using this map and interpolating this value, essentially operating the system under this Pareto optimal point every time. And I showed that if you construct this Pareto control strategy, what I call it, then this is equivalent to the optimal control strategy that we can minimize the long run expected average cost criterion. I did also several simulations to prove these concepts in simulation. To solve this and derive the dynamic programming solution, I used Q-learning. So I had the model of a vehicle, of my hybrid electric vehicle, and I ran it over the same driving cycle again and again using Q-learning. Once I learned the optimal control strategy, then I compared it with a Pareto control strategy that I was able to derive in real time, and I saw that I got the same results. More recently, we applied this approach that was developed several years ago, and we applied this approach in an ARPA NextCar project. I'm going to talk about this project in a while in detail. So we have an Audi A3 plug-in hybrid electric vehicle, and the idea was to improve the efficiency of this vehicle. So we use this approach, and we show that we can have at least 12% improvement over the Audi's controller, the Audi's power controller. Now, our industrial partner, Bosch, in this project got really surprised with this result, and it was too good to be true. So they did a statistical analysis, and they compared the engine operating points that you can see on the left from the Audi's controller with the engine operating points from the Pareto optimal solution. And they show that statistically, we operate the engine in the more efficient BSFC regimes. We talk about the BSFC earlier on. It's the fuel consumption per unit power. And that was the reason that we got these significant improvements. So that was the second stage on my career, working on hybrid electric vehicles and plug-in hybrid electric vehicles, still being at Oak Ridge. And at that time, I saw opportunities with connected automated vehicles. And I thought that using shared information from vehicles, we can essentially take this information and optimize the powertrain or optimize energy, the transportation efficiency. Essentially, what I have in mind was how we can use this information to coordinate the vehicles in intersections, emerging roadways, and avoid stop-and-go driving, and then have benefits in energy indirectly. If you think about it, these are not new ideas. The first time that the automation was sort of appeared in the community was in 1939, when they have in the Futurama, they had a model of the world into the future, and a big sector of this model was devoted to transportation, and they envisioned a fully automated highway system with the cars. Now imagine in 1939 to have a vision like this, having a fully automated highway system. In 1956, GM featured another car 20 years into the future, and they essentially showcased the first concept of a self-driving car. They had, this family driving to Chicago, and they, envision how you can have a fully autonomous car, and while the car drives on its own, the family enjoys a bunch of luxury stuff, like, as you can see in the wild, the dad will fire up a cigar, they will have ice cream and drinks in the car. So that was a kind of, showcasing how the impact of potential having cars to drive on their own. So these are not, new ideas. And the fact that for over the last 83 years, we still haven't been able to get there, it speaks to itself how hard is this problem. So long story short, over the last several years, we developed control algorithms that can use the shared information from the vehicles and coordinate the vehicles in intersections, in emerging roadways, in roundabouts, and improve transportation efficiency. Let me take the next several minutes to sort of give you a flavor about how we can model this problem and how we can address this. I'm going to use intersection as a reference, but this approach can be used for any transportation, any traffic scenario, like merging roadways, roundabouts, you name it. So let's assume that we have 4 connected automated vehicles approaching an intersection without traffic lights. And if the vehicles keep cruising, then they will potentially have a conflict. The area at the center of the intersection that the vehicles can have a potential conflict is called merging zone. And then we define the control zone, which is outside the merging zone. And this is the area that the vehicles can communicate with each other and exchange information. So the problem here is once the vehicles enter the control zone to exchange information and coordinate in a way that they can cross the intersection without stop-and-go driving and without collision. So the idea here is that once the vehicle enters the control zone, first to identify the times that will be entering the merging zone, the time that will be exiting the merging zone, and the time that will be exiting the control zone, getting out of the control zone. And once the vehicle identifies these times, the next task is to derive its optimal acceleration, deceleration in terms of fuel consumption so that to cross the intersection. So if you think about it, we address 2 problems. In the upper level problem, we identify the times for the vehicles to cross the intersection. And this is essentially a throughput maximization problem. And on the lower level problem, we derive the optimal acceleration of the vehicle for these times that they will minimize the energy consumption of each of these vehicles. So now what I'm going to do in the next few minutes is that I'm going to start with the analytical solution of the low-level problem and show you how we can use this solution to define a new problem, formulate a new problem that can solve both problems at the same time. Why we need to do that? The reason is that, as you will see in a while, the low-level solution can become very tedious because it's a constraint optimization problem. And it becomes so tedious that you cannot really solve this online on board the vehicle. So we need to bypass this and have the same solution, but with a different approach. So in our exposition, we model each vehicle as a double integrator. P is the position of the vehicle starting at the entry of the control zone. V is the speed of the vehicle. U is the control input, acceleration, deceleration. And then we add this, the distance SI, which is the distance of each vehicle I from the preceding vehicle K. And this corresponds to the proximity sensor of the vehicle. So this proximity sensor, you can measure the distance from your preceding vehicle. Somebody might argue here that and say, hey, you know what? The double integrator model is too simple to capture a real vehicle. And that argument would be absolutely correct. And actually, I'm going to use this argument at the end to highlight the challenges of using model-based control, just because we have a discrepancy between the model and the actual system. Now, what we're going to do here to bypass this challenge is I'm going to use the double integrator model to derive an optimal control input, the optimal acceleration, deceleration profile of the vehicle. And then I'm going to use a low-level controller, PI or PID controller, to track this optimal trajectory. So essentially, I convert the optimal control problem to a tracking signal problem. And this is how I can bypass the discrepancy between the model-based approach, the model and the actual system. And since I want to derive an optimal solution in real time, that's the only option that I have. This is actually how OEMs design cruise controllers as we speak. Then the next step is to identify the bounds of my control input and my state. So for example, each vehicle has a maximum acceleration and deceleration capability. We need to incorporate this into our modeling framework. And for each time TI naught that the vehicle enters the control zone until the time TIF that the vehicle exits the control zone, we impose a speed limit within the control zone for each vehicle. Then we need to make sure that we satisfy safety constraints. The first safety constraint is the re-end collision constraint, where we require that each vehicle, the distance of each vehicle I from the preceding vehicle K is always bigger than or equal to a safe distance delta I, which is also a function of the speed, in the sense that the higher the speed, the higher the distance that we need to maintain from the preceding vehicle. And finally, we make sure that we don't have a lateral collision at the center of the control zone. Once we get this done, the next step is to formulate our problem, which is minimizing the optimal L2 norm of the control input of the vehicle from TI naught that the vehicle enters the control zone until TIF that the vehicle exits the control zone, subject to all my boundary conditions, dynamics, and the safety, state and control and safety constraints. Now, somebody might argue here again and say, hey, you know what? You told us that you're going to minimize energy consumption and you're minimizing the L2 norm of the control input. How are these two related? Well, if you remember from the first part of the talk, by minimizing transient engine operation, essentially we maximize fuel consumption. So this is essentially what we're trying to do here. We're trying to minimize transient engine operation and give the desired speed to the driver with a minimal with a minimal acceleration, minimal deceleration. So this is how we can get indirect benefits in fuel consumption. Now, to solve this problem, we can use Hamiltonian analysis. And if none of the state and control or safety constraints become active, then we have a very nice closed form analytical solution where the optimal control input is the linear and affine polynomial function with respect to t. The optimal speed of the vehicle is a nice quadratic polynomial function, and the optimal position of the vehicle is a cubic polynomial function of time. Now, A, C, D, and E are constants of integrations that can compute easily from the initial and final conditions. However, if any of the state, control, or safety constraints become active, then things are getting complicated. And just to give you, to outline the idea of this complication, first of all, let's assume that none of the constraints become active from the time TI naught until that the vehicle enters the control zone until the time TIF that the vehicle exits the control zone. In this case, we have the very nice closed form analytical solution that I just showed you before, that can be implemented in real time on board the vehicle. However, if any of the state, control, or safety constraints become active, then what we need to do to address this is to piece the unconstrained and constrained arcs together to satisfy the Euler-Lagrange equations along with the boundary conditions of the system. And then we end up with a set of algebraic nonlinear equations that we can solve on board the vehicle to find out the junction points T1 and T2 along with the constants of integration. Essentially, this implies that we can no longer hope for any closed form analytical solution. We seek for numerical solutions like steepest descent and so forth and so on, which means that we cannot really solve this problem on board the vehicle. That's it. And even if we get a solution, what might happen is another constraint might become active. So we need to repeat this process, again. Just to give you a flavor of the complexity, let's consider that we have the re-end safety constraint, right? Ni of t x of t. If this becomes active, then this causes discontinuities on the influence function of my Hamiltonian analysis, which means that to address these discontinuities, I need to adjoin the partial derivative of my re-end safety constraint with respect to the state of the system by a set of Lagrange multiplier and come up with a system of nonlinear algebraic equations that I need to solve simultaneously. So this is impossible to solve on board the vehicle. We hit the wall when we were working on our Audi A3 plug-in hybrid electric vehicle. So we had to address this problem. Now, how to address this problem? Essentially, the idea is that if I can have my optimal solution, my optimal unconstrained solution, which is a nice closed form analytical solution, without activating any of the state control or safety constraints, I would be happy, right? Because I can solve this problem online. So how can I get this solution eventually? First of all, we start with a polynomial, a cubic polynomial of the unconstrained case. If you remember, this is a nice polynomial that we can get if none of the state controls or safety constraints becomes active. Now, this is from the entry of this polynomial is active between Ti and not TIF, which means that from the time that the vehicle enters the control zone until the time from the vehicle exits the control zone. Now, if you observe this polynomial, we can make three observations. First, this is a real value function. Second, this is differentiable. And third, this is strictly increasing, which means that this is a one-to-one function, which means that the inverse of this function exists. We call the inverse time trajectory of the system. And to compute this, the inverse of this polynomial, the cubic polynomial, you can use Cardano's method. This is a pretty straightforward way to find the inverse function. Now, if you look at the time trajectory now, this is the inverse of this polynomial. The time trajectory gives you the time of the vehicle within the control zone at a different position. Now, if we evaluate this time trajectory at the exit of the control zone, then I end up with a function with respect to phi, and I can use the phi's to change the shape of my time trajectory, which means that I can use the phi's to minimize the time that my vehicle exits the control zone. Now, if let's assume that we have all the time trajectories of all the vehicles within the control zone, right? So let's assume that all these black lines are the time trajectories of the vehicles that exist inside the control zone. These are the vehicles that crossing the merging zone of the intersection. These are the blue lines. These black lines are the time trajectories of vehicles that going on the same direction with our vehicle. Now, once the vehicle enters the control zone, what this vehicle has to do is to draw this time trajectory and avoid intersecting any of the existing time trajectories within the control zone. If we do that, it means that we do not activate any of the safety constraints. So once we derive this, if the vehicle can derive this time trajectory, then it can inverse back, right? And come up with a polynomial function that you can see on top of the slide, which means that we get the solution of the low-level control. So essentially, conceptually, with this approach, we can solve both problems, the upper-level problem and the low-level problem, without activating any of the state control or safety constraints. So that's the idea schematically. Let's put this in context now, in mathematical context. So we start with a polynomial, which is the analytical solution of the low-level control. We use Cardano's method and we take the inverse function, and then we evaluate this time trajectory with at the exit of the control zone. And we come up, we essentially define a new function, phi, that which is essentially the new objective function. We're going to minimize the function phi that will give you the time that the vehicle will be exiting the control zone with respect to the coefficients phi. Now, before we formulate the problem, we need to make sure that we satisfy a bunch of boundary conditions, like the initial and final position of the vehicle at the entry and exit of the control zone, the speed of the vehicle at the entry of the control zone. This is, initial conditions, the influence fraction of the exit of the control zone, along with the position at the entry of the merging zone. Those are boundary conditions. So when I draw my trajectory, I need to make sure that the trajectory satisfies these conditions. And at the same time, if you recall, I don't want to activate any of the state and control constraints. So when I derive this time trajectory, I don't want to activate my maximum and minimum speed limits or the maximum and minimum control inputs, and I want to make sure that I do not activate any of the safety constraints. Now, given all my set and this framework, I can formulate my problem, which is minimizing the time trajectory of the vehicle evaluated at the exit of the control zone, subject to my initial and final conditions and all my inequality constraints. And then at the same time, I allow my vehicle to explore other lanes. And I do this, so I just create the occupancy set of each of the lanes and make sure that I don't have any conflicts in any of the other lane. Now, to solve this problem, the question is, can I solve this problem in real time? It turns out that the objective function, the time trajectory evaluated at the exit of the control zone, is a convex function. And also, all the set of equality and inequality constraints are affine convex functions, which means that if I apply the Slaughter's weaker condition, I can show that there is no duality gap in this problem formulation that I just described, which means that we can solve this problem in real time. So just to give you a flavor of the results of this framework, we have applied this and variations of this framework in different scenarios. This is one of the examples that we use in our scale city. You can see the cars, trying to cross the intersection without stop-and-go driving by, deriving the optimal control input at the entry of the control zone. We have also implement this in a corridor, including an intersection, merging roadway, and roundabout. You can see how the cars all together, by the time they get into the control zone, they derive the optimal control input, and they can cross all these conflict points without stop-and-go driving. We also implement this in our demo vehicle. This is, as I said before, an ARPAI project, Next Car. We completed this program last year, last December. The objective here was to use connectivity and automation and improve the efficiency of the Audi by 20%. The project was led by University of Delaware in collaboration with Bosch, Boston University, University of Michigan, and Oak Ridge National Lab. We did several field testing in M-City at the University of Michigan. What you will see here is the Audi in the field in M-City, but however, the Audi is interacting with a bunch of virtual vehicles. That's the black vehicles that you can see on the left. On the top is the baseline scenario without connectivity and automation. On the bottom is the scenario with connectivity and automation. So as you can see on the bottom, the Audi, as the Audi approaches the merging zone, it coordinates with other black vehicles, the virtual vehicles, and gets into the merging zone without stop-and-go driving. On the top, the baseline scenario, the Audi has a black vehicle, a virtual vehicle ahead, so it has to wait until the black vehicle departs in order to get into the merging zone. This is the typical scenario that we encounter today when we have on a wrap a yield sign. So now the Audi can get into the merging zone. We also did several vehicle-in-the-loop testing at Bosch Farmington Hill facilities with our collaborators. We essentially put the car on a chassis dyno, and the car drove through a virtual environment interacting with other vehicles. On the left is the baseline scenario without connectivity and automation. On the right is the scenario when all the cars are connected and automated. And then you can see how we have smoothed out the speed profile of the vehicle since we have eliminated the stop-and-go driving, right? Now we have stretched essentially the speed profile and make it a freeway driving. So essentially the Audi, when it arrives in the merging roadway, can coordinate and cross the merging roadway and so forth and so on. And we have this particular smoothing out of the speed profile, which result in benefits ranging from 14% all the way to 35% improvement. So just to summarize what we have talked about this so far, we discussed about model-based control approaches, and we show that we cannot always facilitate optimal solutions with performance guarantees just because we have the discrepancy between the model and the actual system. If you recall, I used the double integrator model to capture the dynamics of these vehicles, and then I had to essentially use a PID controller to capture this discrepancy. In the supervised learning, on the other hand, you cannot always facilitate robust solutions with performance guarantees using offline data only. When I work with a fuel injector characteristic curve, I had to combine offline data with real-time control in order to address this drawback. On the contrary, using reinforcement learning techniques, we can really apply reinforcement learning techniques directly to an actual system, because this might impose some implications on safety and robustness. For example, when I used direct reinforcement learning on the engine problem, I might have sometimes to stall the engine just because I was exploring actions outside the feasible domain of action. And even we're very careful to identify for each different state the feasible action space. This action space might change. For example, in an application like the vehicles, if you operate the vehicle in Nevada and then you operate it in Michigan or in different state, there are different environmental conditions, and the action space can change. Even on the same state, depending on the the temperature and the humidity, this action space can change. So the idea is, can we combine both learning and control to address these challenges? And before we do that, we need to be able to separate the control and the learning. So let me, in the next 7 to 8 minutes, let me try to highlight this idea. That's a pretty new idea. So we consider that we have an actual CPS and any cyber-physical system, and we have some disturbance with this system, and we have some noise observation of the actual CPS. And then we have a model of this system, any model. And we operate both systems at the same time. So we control the actual CPS and the CPS model at the same time. Now, the idea is to establish a new information state that we can use to derive the optimal control strategy of the system offline. Now, this information state will have information from both the actual CPS and the CPS model. So if I use this information state offline to derive an optimal control strategy using only the model that I have available, I won't have the information of my actual CPS. So it means this implies that I'm going to parameterize the control strategy that I'm going to derive offline with respect to the different realization of the state of my actual CPS. Now, what's the idea here? Once I use my model to derive the optimal control strategy using the information state, which means that I need to parameterize my optimal control strategy with respect to the realization of the state of my actual CPS, then I'm going back to my system, my initial system, and I apply this control strategy to my actual CPS and CPS model. And as I start collecting data, I'm learning the information state. Now, what I'm going to show you in a while is that once we learn the information state online, then the optimal control strategy that we derived offline becomes optimal for the actual CPS. Now, let's get into more technical details to see this concept. Let's assume that we have an actual CPS, a cyber-physical system with decentralized information structure. So it means that we have a system of systems. For example, you can imagine that this is a fleet, a number of connected automated vehicles that they're trying to cross the intersection. And the XT hat is the system, the state of the system, WT is the disturbance, and UTK is the control of each of the subsystems. So UTK, you can imagine that this is the control input of each individual vehicle, acceleration, deceleration. XT is the state of my system, position of the vehicle, and speed. XT hat and WT are random variables that are defined in appropriate probability space. And then for each of these subsystems, we have a noise observation. So imagine that every single CAV can observe the state of the system with some noise, because there's some noise when you measure the distance from the preceding vehicle. There is some noise or error when you have the information about the position of other vehicles, and so forth and so on, right? Now, we have the actual CPS, and the problem here is to minimize the expected total cost of this system. And in this cost, we have ST, which are some measurable cost functions. You can imagine that this is the travel time of each of these vehicles, or of fuel consumption, or a combination. Now, to solve this problem, as we discussed in the last chapter with connected automated vehicles, we can't really do that because we don't have, the model. We don't know the dynamics of our actual vehicles, and we will use models. We use the double integrator to do that. So we assume that we have also the double integrators, the CPS model, and we operate the actual CPS, the actual vehicles, and the double integrator models at the same time. And then the idea here is to establish a new information state for this system. This information state is the joint probability distribution of the XT, the state of my model, and the state of my actual CPS, given all the data of my model, which is the information structure of the model. Now, what is delta t? What is the information structure of the model, delta t and lambda t? Now, imagine that, remember that I mentioned that this is a decentralized system with a decentralized information structure, which means that there is an n-step delay information. For example, if a system, any of these subsystems have an observation or an action, this observation and action will become known to any other system after n time steps. So there's some delay, and this is typical in emerging mobility systems or other CPS applications. For example, in the cars, when we exchange information, there's some delay between this information. So now delta t is the common information about all the subsystems, all the common information about all the vehicles, and LTK is the private information of each of these vehicles. Delta t, the per delta t and lambda t is the information structure of my system. So I'm going to use this information state and go offline, pick up the model that I have and solve this problem offline to derive the optimal control strategy. Now, since this information state is a function of the state of my actual CPS, and I do this offline, I don't have any information about my actual state, which means that when I derive the control strategy offline, this control strategy will be parameterized with respect to any realization of my state of my actual CPS. Now, if we take a step back now for a moment and think about what I have done so far, there's nothing new. The only new is that I have added an information state which is parameterized by the realization of my actual CPS. But typically, this is what I do today. I'm using a model, I'm deriving an optimal control strategy offline using the model, and then I take this strategy and apply it to my actual CPS. So I'm now taking this control strategy that I derived offline, and I'm going to apply this to my actual CPS and the CPS model. However, as I apply this and I start collecting data, I'm start learning the information state of my system in real time. And once I learn, after several some time, I learn this information state, then my control strategy will become optimal for my actual CPS. However, before I show you this result, I need to make sure that I can do this exercise. I can separate my control and learning, so the information state essentially does not depend on the control strategy. So the first result, shows exactly this, that essentially the joint probability distribution of the state of my model and actual state, given all the data, is indeed an information state, the evolution of which does not depend on the control strategy. What does it mean? It means that every time, once my information state evolves, this does not depend on the choice of the control strategy, but on the realization of the random variables of my system, which implies that I can separate my control, state estimation from my control design. Using these results, then I can show you. I can go back. Remember that this is the problem that I want to solve at the beginning. I want to minimize the expected total cost of the actual CPS. Instead of solving this problem using my new information state, I'm going to solve this problem, which is essentially I have added a penalty function between any discrepancy of the state of my model and the state of my actual CPS. And then the following result says that once I solve this problem, the optimal control strategy is also optimal for my initial problem of my actual CPS. Just to give you the intuition, I'm not gonna go through the proof. This is available online, but just to give you the intuition, we're solving this problem using the offline using the information state of my system. Now, when I solve this problem, for each realization of my state of my model, I derive an optimal control action, and this is parameterized with respect to different realizations of my state of my my actual CPS. So instead of having a given value of UT of the control action, I have a vector of values corresponding to different realization of my actual CPS. Now, when I apply this to my actual CPS and the model, and I start learning the information state, once I learn the information state, then I'm picking up control actions that will yield realizations of my actual CPS that minimize this cost. Essentially, if you can think about once this happens, then eventually the two problems, the control strategies of two problems become the same. As we speak, we applying this framework to the problem of coordination of vehicles on specific scenarios. If you remember, that was the initial cost function that I wanted to use. And this cost function resulted in a nice closed form analytical solution. Essentially, what we're trying to do now is to enhance this initial problem one with a new cost function and come up with a parameterized control strategy that we can learn online. We hope that this approach can be applied to several CPS applications with a decentralized information structure, when we have essentially a large volume of data that is added to the system gradually and not altogether in advance. So in these particular problems, we can really, we have several challenges using either learning or model-based control approaches. So we believe that this approach can help bridge this gap. Applications include emerging mobility system, network control systems, communication networks, power systems, social media platforms for operation of borders, of robots, you name it. So with this, I would like to thank you for your attention, and I'd be happy to take any questions.
Thank you, Andreas. Very interesting, excellent talk. So for the Q&A session, we have Dr. Johannes Betts, Ziji, and Yi, who will take your questions.
So yeah, thank you very much for a very interesting talk. I think you covered a wide variety of topics where I hope you get a lot of questions. And we have the first one from Yi. So Yi, you can ask the question.
Sure. Hello, Professor. For the upper level control problem, can you talk more about the merging zone, like the constraints in the merging zone, or what is the difference between the merging zone and the control zone? I'm pretty new to this area, and thank you.
Absolutely. So essentially, in the control zone, this is an area outside the intersection that you're going to control, right? So we have a boundary, and this boundary is specified by the physical constraints of the system. So, for example, the vehicles can communicate up to a certain point with each other, right? So once we identify these limitations, then we define the control zone, inside of which the vehicles start communicating with each other and exchange information. And then given this, we need to make sure that they don't collide with each other on the same road. So we have the rear end collision avoidance constraints, and at the same time, they cross the intersection, the merging zone, without any lateral collision. So that's the two main constraints. Now, the upper level problem is, to identify for the vehicle the entry of the merging zone, the exit of the merging zone, and the exit of the control zone. Once we fix these times, then the low level problem is to derive the optimal acceleration, deceleration of the vehicles to cross the intersection without, in terms of minimizing fuel consumption of each individual vehicles.
Okay, thanks for the clarification, Professor.
Absolutely.
Thank you very much for answering this question. Since we have no other question yet here, I would like to ask one question, Andreas. This is a little bit a high-level question, and I think you can elaborate here a little bit more. So you showed that we can solve the intersection with low energy and with high throughput, right? And in the future, actually what we see here, right, in the setup. So in the future, we have like a lot of autonomous cars, and the development right now of autonomous cars like perception, planning, control to make the cars drive completely free with any high level steering or something like that. So when you look at your research and you showed us the controller you created, can you elaborate where the most impact comes from? Is it the path that the car is then planning? Is it the velocity that the car is planning? Is it like the final controller, the overall controller setup? Or is it even the behavior the car is planning? Right? So perhaps just elaborate a little bit more where you think finally it comes down to this point where you figured out in your research that creates the impact?
Great question. Thank you for asking this question. You are absolutely correct. We dig into this question for quite some time to understand where these benefits coming from. Yeah, and to help me answer this question, I'm showing you this video. On the left, this is the baseline scenario, what we have today in our transportation network: no connectivity, no automation. And then we have to stop on stop signs, on traffic signals, on merging roadways. And this is, you can see the speed profile of the vehicle with a stop and go driving. On the right, this is the utopian scenario, something that I think we're gonna have to wait until we see it realized in our transportation network. But you can see how we have smoothed out the speed profile. And then given this, we have benefits ranging from 13 all the way to 34%, right? So I wonder, how are these benefits, where are these benefits coming from? And I did a very simple exercise. I went to my car and I checked the window sticker of my car and say, you have 35 miles per gallon for highway driving and 28% or 27 miles per gallon for city driving. And I compare the difference. This is about the same range, 30 to 25, 30 to 35%. If you do the same exercise for your car, you will see the difference is about that range. It means that once you stretch the speed profile of the vehicle and you make it a freeway driving, this is where all the benefits are coming from. Of course, in this particular RPI project, when we did, we also did powertrain optimization. So on top of the communication of and smoothing out the traffic flow, we did a better power management control on the powertrain of the vehicle. And we were able to get about 12% improvement. This is in addition, but the majority of the benefits is coming by smoothing out the traffic, the speed profile of the vehicle. If ideally we could leave home and go to our final destination without stop and go driving, without coming to a full stop whatsoever, that would be the ideal scenario. I'm not sure if I answered your question.
No, you answered it perfectly, because that's what in my research, I did like some energy optimization too. And that's also what I figured out, right? And I think what we underestimate right now in autonomous driving development and software development is exactly this, because that's where you get the impact afterwards. Great. Okay, so we still have time for questions. Please write it down in the chat or in the QA session, and I can ask them for you. Meanwhile, I would address the next question from my side. Let's talk about some application point of view. You tested everything on a car, and you also told us before, hey, we cannot solve this problem on the car because we don't have the computation power. So when you solved the problem, what kind of computer did you use, and what was the calculation time of solving this problem? Just to give us some numbers and ideas what we are dealing with, because this is like a very big and complex problem, right?
Absolutely, yeah, you're absolutely right. So the first time that we solved the problem and we sent it to Bosch to implement this in the Audi, I got a call and they start yelling at me. And they say, you know what? There's no way that we can implement this on board on an Audi. And they gave me an example. First of all, one of the solutions included the 4x4 matrix inversion. And they told me, you need to give us the analytical solution of this inversion. We can't really invert the matrix. So that was a reality check for us, and we went back to the robot and start seeing how this can be implemented. Eventually, the problem that you see right now can be solved in real time, because essentially what you do, let me try to go back to the conceptually. I like to use this this graph, because it explains very nicely, how you solve the problem. So essentially, this is the problem. The vehicle gets into the entry of the control zone. You have a coordinator, an intersection protocol, we call it, and this intersection protocol records all the time trajectories of the vehicles inside the control zone. So once you enter the control zone, the vehicle accesses this intersection protocol and all the existing time trajectories. These black lines are the time trajectories. So what the vehicle has to do is to draw this line.
Yeah.
Just avoiding intersecting. So essentially, you can translate this solution by a very simple search problem, which starts with trying to find out what's my exit time without activating any of the state and control constraints. So eventually, you can do some very simplistic analysis and computations to get these points. Essentially, you try to find out a polynomial metamodel with a specific form, right? It's just fitting a curve. That's what you're trying to do. Once you try to fit this curve and you create this time trajectory, then you inverse back and you have the solution for both problems. So this is the trick that we did with the Audi, and we were able to, solve the problem in real time. However, before you get to that point, you need to make sure that at least on the theoretical, from the theoretical perspective, you're doing the right thing. Your problem gives you the capacity to get the solution online and so forth and so on. But to get the exact solution, you can definitely find simple numerical methods that can implement it in real time and get your result.
All right, great. So we can sum up here. We don't create a super huge optimization problem, put it on a supercomputer with some smart solution. We can even bring it on the car finally. Okay, great. Thank you very much. I think we don't have any more questions. I don't see any. Yeah. Okay, then I would host a discussion. I would, of course, encourage Andreas, if it's fine, somebody has some questions, a question for you, afterwards, you probably will answer. Thank you very much for having you, and I would lead the last words to Raul. Thank you,
Johannes, for leading that Q&A session. And thanks so much, Andreas. These are actually the Q&A actually cleared a lot of my questions too. So, and thanks everyone for joining us today. So please tune in next Friday, February 4th at 10:30 a.m. for our next Grasp on Robotics talk featuring Stefanos Nikolaidis from University of Southern California. And his talk will be on towards robust human-robot interaction, a quality diversity approach. So Stefanos plans to be on campus next week to present his talk in person in Wuhan Auditorium. So his talk will also be live streamed on Zoom. So for more upcoming events, be sure to follow us on social media and check out our website. Thank you again and have a wonderful day.